Okay, good night to everyone, all of the participants, both in the Zoom link and also in YouTube. Today we have a very special guest, but before that, I would like to give the word to Roxy, so she can give us an introduction.
Hello, good night to everyone. It's really nice to have you all here, and we really appreciate joining us. I would like to give a quick introduction about what is Space Generation Advisory Council, the organization we are part of, and the ones that are letting us do this kind of events. Space Generation Advisory Council, in support of the United Nations Program on Space Application, is a non-governmental, non-profit organization and network which aims to represent university students and young space professionals between the ages of 18 and 35 to the United Nations, Space Agency, industry, and the academia. We have been doing a lot of webinars, workshops, and in the open course we are now running, Angel Arcia and myself. And it's been really great. We have done the introduction to NASA and its future mission webinar. We also did the Mujeres Conciencia or Women in Science webinar in Nicaragua. We had invited Dr. Sandra Kaufman to join us, and we are running the second edition of the open course Introduction to Space Engineering, and hoping to start soon the third edition of the course. So it's been a pleasure to be working and doing all these webinars and workshops for all of the participants we have. And now I would like to give the word to Angel Arcia so he can go ahead with the webinar.
Thank you, Roxy, for this amazing introduction, as usual, and also for the support of Nicaragua and Panama to all of these activities. Today is our fourth guest of the Space Speaker of the Month series. His name is Ulises Eduardo Núñez. He's originally from Santiago de Veraguas in Panama. By the way, that's the same province which I am coming from. I was born. And he did his bachelor and master's in aerospace engineering at Georgia Tech. And he's currently a graduate student at the Space System Design Lab, also at this university, Georgia Tech, under the advice of Dr. Glenn Lindsay. His research interests are in astrodynamics and spacecraft guidance, navigation and control, GN&C. And his current work is related to probability theory and quasi-random number sequence generation to spaceflight mechanics, dynamics of spacecraft relative motion, and collision avoidance in spacecraft formations. So Ulises, as we said in previously, it's an honor to have you with us, and go ahead with your presentation.
All right, Angel, thank you so much for the introduction, and it's quite the honor to be with you all tonight. Can you hear me well?
Yes,
we can.
Okay, let me go ahead and share my screen with you. Yeah, as I said before, good evening, everybody. My name is Ulises Núñez, and I am, sorry, better turn that off. Now I'm a PhD student at Georgia Tech under the supervision of Dr. Glenn Lightsey at the Space Systems Design Lab. Today, it's a huge honor to present to you the topic relating collision probability and missed distance indicators in spacecraft formation collision risk analysis. This work is motivated by interest in realizing sustainable and practical spacecraft formation flying. So before we get too much further ahead, I would like to define for you what formation flying is. Spacecraft formation flying is defined as a set of more than one spacecraft whose dynamic states are coupled through a common control law. This implies that at least one member of the formation must track a dynamic state relative to another member of the formation. And the control law, the inputs, the control inputs, the thrust inputs, etc., must depend on the state of the other members of the formation. So, some examples of spacecraft formation flying include rendezvous and docking. For example, the spaceship that is doing rendezvous, which is just meeting with another spacecraft, in this case, the International Space Station, and docking also. In this case, we see that we are controlling the relative position between these two in a way that gets them closer to one another. That's an example of formation flying. Another example is formation keeping proper. For example, the MMS mission, the magnetospheric multi-scale mission, which studies the Earth's magnetic field and its interaction with solar wind. This is a formation that has the shape of a tetrahedron, and it's essentially like a pyramid, and they keep this relative geometry. So this would be an example of formation flying. These entities are not examples of formation flying. For example, individual spacecraft, such as the Hubble Space Telescope, is a single monolithic spacecraft, so it's not a group. And also, surprisingly, this is the constellations of spacecraft are generally not considered to be formation flying, because although they do operate in a group setting, they have to keep their slots, basically this box of physical space that they need to occupy. They do it in an absolute sense, and they don't really control their position relative to one another. And so they're linked to each other in an operational way, but not really in a dynamic way. So now we'll go ahead and talk about some of the benefits of spacecraft formation flying. So in the scores from that you guys have been taught by Angel in the course Introduction to Space Engineering that Angel has been teaching, he has been introducing you to spacecraft systems engineering and the idea of mission design attributes, or abilities. So spacecraft formation flying is attractive because it adds new layers to space mission architecture traits beyond those of traditional single spacecraft missions. Specifically, formation flying can give missions further flexibility, specifically in the areas of modularity, because you have physically distinct assets that are they operate next to each other, but they're in fact distinct pieces of equipment. Adaptability, by having gradual system implementation. Potentially you could, in this formation, you could deploy each of them individually and have gradual ramping up the performance that you're supposed to get from the group of spacecraft. And also maintainability, because you can, in the event that any of these spacecraft failed or had decreased performance, you could think about replacing them. So it also, spacecraft formation flying missions can potentially have more robustness. That's another improvable system attribute, namely because it inherently has more fault tolerance, because the deterioration or failure even of an asset of an individual spacecraft doesn't mean that the mission necessarily needs to end. So as that's good, we want that, because there's no really easy way to fix failed or broken assets in space. And also because it can also give more probability of success, so you inherently can have more reliable systems. Additionally, there's many scientific applications in formation flying. So, namely, formation flying can allow missions that require high precision instrumentation. Two examples of technologies that are enabled by formation flying are occultation methods and synthetic aperture observations. So, for example, in occultation methods, a shade spacecraft is is put between a target, which is a star generally, and it can dim the brightness of that star. So it gets between in the line of sight between a star and an imager spacecraft, a telescope. And this can have many applications. For example, in the star shade concept, this can be used to detect exoplanets. There's also concepts for instead of having a shade, to have basically a spacecraft that filters light and is able to still that can enable direct imaging of the surface of a star by essentially acting as a filter of the brightness of the star. So this is an example of a mission concept that's enabled by formation flying. Another mission concept is that of synthetic aperture radiometry, which I'll explain this in this picture. So each of these small circles, the red and blue circles, are the field of view of one individual spacecraft. So if you had one imager or telescope or whatever, this is about as much area as you could cover. However, with imager instrument. However, if you have an array of spacecraft that are all pointing toward the same target, you could add all of the measurements through sensor fusion and synthesize an aperture that's this big. So that's a very promising idea, because it means that if we require arbitrarily large apertures, we could just send a group of spacecraft, potentially having coarse resolution, not very high resolution, and we can synthesize a bigger instrument. So that's very promising. Some of the applications of these, there's many other mission concepts that could be enabled through formation flying, and there's many applications to these ideas in areas such as astrophysics, gravitational wave detection, and exoplanet detection, and earth science such as gravity field recovery, weather forecasting, climate monitoring. So that's a very helpful thing in this day and age when there's concerns about the climate of the biosphere on planet Earth changing. So we can measure that more precisely with things like that. And also heliophysics, sun science, such as recovery of the magnetic field around the sun, studying coronal mass ejection, and just plainly imaging the resolution of the sun's surface with high resolution. That would be really transformational, the kinds of science that could be done with these mission concepts. So with that in mind, that's just a flavor. I could go on and on about all the benefits of spacecraft formation flying, and so I'm just going to, for the rest of the talk, assume that formation flying is something that we want to accomplish. Is a worthy research endeavor. So with that in mind, the thing that we want in any mission is for the mission to continue to exist, for the mission to survive. And so the number one, I guess the most obvious pitfall with a group of spacecraft flying together is the risk of collisions. And so the subject of this talk has to do with with quantifying collision risk. And so in this, there's two kinds of collision risks. in spacecraft formation. First one arises from external kinetic threats or debris. As you probably know from, you have heard many times in this course with Angel, external debris are a serious threat to any spacecraft in the Earth environment, in any Earth orbit, really. However, this is not the only collision threat to a group of spacecraft that fly in formation. Additionally, there's a significant risk of collision among agents that are flying together in formation because they may drift toward each other or because they may maneuver in a way that leads them to come closer to each other. These threats are constant, and so safety concerns must be balanced with wise propellant usage. We can't just fire our thrusters as much as we want all the time. So this presentation focuses on managing the risk of internal collisions. And so for now, I'm going to assume that we're not going to be talking about external debris. So work in spacecraft in collision avoidance in spacecraft formation flying can be broadly categorized into passive and active schemes. Passive schemes focus on the design of passively safe relative orbits, with maneuvers only indirectly addressing collision risk. Active schemes focus on monitoring collision risk, of having a way of estimating how much risk there might be of spacecraft coming together, checking safety criteria violation, namely having a decision-making process to make sure that to make the decision, do we need to make an action, a corrective action or not? And when needed, planning and execution of dedicated collision avoidance maneuvers. This work focuses on active collision avoidance methods, which are characterized by their collision risk indicators. In these charts, you see conceptual illustrations of probability density functions, or PDFs. That's not the Acrobat document reader. No, this is basically for in order to continue this conversation, we have to talk about the idea of random variables. Because we do not know the position and relative velocity of spacecraft perfectly, we can only know where they are in a statistical sense. And so when we talk about probability density functions, we're talking about a mathematical model that describes the distribution of the error of that we have, and there's some assumptions baked in there, but generally we can associate the error distribution with the outcome of an estimation process or navigation. So when we're talking about separation or collision probability, really we can only talk about those in a statistical way. There's no way to say with 100% certainty that we know where something is. And so one type of collision risk indicator is missed distance, which is a statistical description of the physical separation between two agents. In this case, agent J is the origin of this reference frame, and agent I is expected to be at this position. And it's the most likely place there it might be, but it can really be anywhere. And so there's other ways in which we measure separation, but this is just one of the most popular ones. And the other type of collision risk indicator is the probability of collision, which is the probability mass at any, basically the integral over regions of a probability density function is a probability measure. And in this case, we're saying that if the spacecraft I really is anywhere in this circle, or if it's in three-dimensional space as a ball in the around the origin, then the two agents are said to be colliding. And so, in this case, the probability mass in this region is what we call collision probability. So the collision risk generally is mitigated by setting constraints in an optimal control problem in terms of this indicators, either miss distance or separation, and collision probability. The main intention of this work is to check if collision risk assessments, that means descriptions of whether or not we expect two agents that are flying information to be colliding, whether they are consistent, if they are based on either miss distance or separation, and collision probability. In other words, we would like to understand whether or not conclusions drawn from one class of collision risk indicator hold when using the other indicator, and whether or not they can be used interchangeably. Investigating this question has many benefits. So generally, as I said, you only have, when you're using your control law to avoid collision, generally it is formulated in terms of either collision probability or separation, but not both. And so we would like to understand what the relationship was if we use one over the other. And so, yeah, so doing this is a step toward bridging these different philosophies of active collision avoidance methods. Without any further interruption, let's go ahead. So this presentation is organized as follows. First, we will formalize the notion of collision. We will do this using the language of topology. Next, we will also define instantaneous or kinematic probabilities of collision, which we will define as KPCs. We will make a distinction between true or three-dimensional KPCs and projection or two-dimensional KPCs. This result will be validated through Monte Carlo simulations. We will present a theoretical result on this, by the way. We will also move on to talk about collision risk assessments and how they compare when they're based on either collision probability or miss distance. And finally, we'll talk about some results. All right, so let's get started. We first will discuss the idea of a characteristic length or hard body radius, which is which we define here to be the furthest Euclidean distance from the center of mass of an agent to any point in its body. So then we make the hard body radius assumption, which basically says that that the body of agent I, say, can be approximated by a ball that is centered at the center of mass of agent I. This is a conservative assumption that is going to simplify for us the definition of collision events. So you should bear in mind that these are surrogates for the size of the object, and they are not position PDFs. With these notions, we define a collision event as the condition when distinct agents occupy portions of the same volume of space at the same time. That is, when their circumscribing balls have a non-empty intersection. Alternatively, we can also define, say that a collision occurs when the distance between the centers of mass of both agents, say agent I and agent J, is less than the sum of the hard body radii. So that's how we define collisions formally. Now we will delve into defining probabilities of collision. There's a lot in this slide, so we'll stay here for a little bit to explain some ideas. So this gray contour you see represents a three-dimensional relative position PDF. So what you see is only a contour, but in reality, there's a non-zero chance that the separation between two agents is infinite, while the probability of that happening is infinitely small. So anyways, so the red region is the true collision region, meaning that a collision event, the way that we defined in the previous slide, occurs when the actual position between agents is in that ball. So therefore, the kinematic probability of collision, or KPC, is defined as the probability mass of the relative position PDF that is inside the collision region. The plane with gray grid is called a projection plane. It is called that because the relative position PDF can be projected onto that plane. Then we can define the projection KPC as the probability mass of the projected relative position PDF that is inside the projected collision disk. The reason for making this distinction between true and projection KPCs is that before we compare miss distance and collision probability waveforms, it is important to understand if it makes sense to characterize collision risk as approximated by a projection KPC. In the literature, several authors conceptualize collision risk as approximated by various projections, and so we want to know if those approximations are adequate. The main theoretical result presented in the paper is that every projection KPC is an overestimate of the true KPC. What that means is that if we take a collision probability on a plane, any plane that is greater than the true value that would happen if you were using a three-dimensional PDF. It is easy to see why that is, because a projection in three-dimensional space really is an integral over an infinite cylinder versus an integral over a finite area. And so that's a very interesting result that we found, and it has important implications for research in collision avoidance, and that's why we wanted to go ahead and confirm these results through simulation. This figure that you see is a sample, a statistical sample of a given probability density function. So we have a lot of particles in the sample. We have 320 million particles in the sample. It's a pretty big sample. And the reason why we're using samples that big is that because it's so hard to replace any assets in space, generally there's a very low tolerance for catastrophic events. So in this case, even 1 in 10 million collisions is even a chance of 1 in 10 million collisions is a risk that's too high to tolerate sometimes, which is why we tried to do a sample that was really large in order to see if we reproduce these results. So we're not going to go into much detail on this, but basically the result is in simulation, we have this purple waveform is the three-dimensional collision probability waveform, and these are the green waveforms are various projection probabilities of collision, and you see that they're varying over time because the statistics of the error evolve over an orbit. And so we see that the sample results, the results in the asterisk, converge only to the true collision probability, and they do not converge to the projection probabilities of collision. And so we see that in any coordinate plane, the XY, the XZ, and the YZ plane, that just the sample results do not converge to projections. But also in this other chart, we see probabilities of collision normal to the mean relative position and the relative position rate. We see that the true risk is lower than as would be seen by a projection. And that has very interesting implications, because this is actually a kinematic result. Here, this is shown for two spacecraft that are orbiting around each other, but in reality, results like this would apply for any two objects that are in proximity. For example, submarines or UAVs or cars, or really anything, you would see this behavior. This result is significant because if we are using probabilities of collision as a risk mitigation criteria, then if we are using projections, then certainly we have a representation of risk that overestimates how risky the situation really is. And so in space, that's really important because we are resource constrained. There's a correlation between onboard propellant and mission lifetime. So we can't really be burning all the time. So this is good because this gives us basically more tolerance for risk if we wanted to. These representative simulation results also are going to serve as a transition into the next area of contribution in this presentation. We use the notion of consistency of collision risk assessments to refer to the intuition that when two agents are close, by the way, the axis on the right that has orange color, it's really a relative separation. So when you have local minima of that means when you're closest together. When that happens, you would expect that you would have highest collision risk. And when you are far apart, you would expect that you have lowest collision risk. And that's actually not what you see. You actually see the opposite in this example. You see that when you have highest separation is when you have highest collision risk. And when you have closest approach, closest separation, then you have lowest risk of collision. And clearly this picture is inconsistent. Like, we are not getting the same information from relative separation and collision probability. And that's a problem because, like I said, generally we only use one type of indicator over the other. So we do not want that. And so we proposed a few separation measures that, in the hopes that they would be consistent and with having a more physically meaningful interpretation and that we could use in Octon. So in this case, we proposed this. So this contour that you see, the black contour, is a 3 sigma contour. That means that this position is 3 standard deviations away from the mean. And we would like to welcome the former liaison of the Panama, of the cabinet to the Panama Canal and vice versa, and a representative for the Metro, Mr. Roberto Roy. It's a pleasure to have you tonight with us. So here, in this case, this is a point on this contour that is closest to the origin being somewhere far away over here. And equivalently, we also have another way of defining minimum distance to the origin. This contour represents the chance that 99.73% of cases are within this contour away from the mean. So in a sense, these 2 points could tell us essentially if we are close or not, as opposed to expected relative position, which, like we saw, that separation measure really wasn't good when compared to collision probability. Another measure that we see that we defined is the 99.73% minimum distance right here, which, basically what we did is that we grabbed all 320 million particles in the sample and we picked the point so that 99.73% of cases are higher than that. So maybe if we track this point over time, it can tell us something that's consistent with probability of collision. So we will, for this example, for these examples, we're going to look at Clohessy-Wiltshire dynamics. It's a very simple model of relative orbital dynamics. It assumes a circular orbit for a chief and small separation around the chief for a target spacecraft, for a deputy spacecraft or a chaser spacecraft. And so we consider different dynamic cases. We consider the case when we do not have Z motion, when we don't have out of plane motion, and other dynamic cases. I'm not gonna go here to explain other than to say that we explored these results over a wide variety of dynamic cases. And so what we see here, the first result that we find is to rigorously validate sample convergence, that basically this sample that we see here in the statistics that we're able to glean from it and the probabilities that we compute actually converge to the truth in what we assume to be the truth. And in this case, and you see on the left the correlation coefficient between a sample and true KPC waveforms. You can think of this as the inner product or as the dot product between two functions, or the cosine of the angle between two functions. Really, that can be defined. And so you can see that it does approach one, in both in a biased and an unbiased sense. And so we can say that to within a constant sample and true collision probability waveforms converge to each other. On the right, we see that the agreement was to within 3% magnitude. So for all intents and purposes, these samples that we are making actually are true, are an accurate representation of the truth of the process that we are assuming. The second result that we see is to rigorously validate sample convergence to the true KPC. On the left, you see the correlation coefficient. Actually, I got myself mixed up. So the second result is to rigorously validate that sample KPCs do not converge to projection KPCs. This is shown by how the correlation coefficient between sample and projection KPCs actually does approximate one. So basically the angle between these two functions is 0. And that doesn't really happen for any other projections that are all over the place. We don't really see convergence in that sense. And so we can really validate rigorously the main theoretical result of the paper, that a conclusion from the theorem that we proved is that projection KPCs are overestimates of the true KPCs. And so if the projections do not convert, if the sample KPCs do not converge to the projection KPCs, then we have demonstrated this rigorously. Over a wide variety of dynamic cases, over a wide variety of dynamic cases. So the third and final result is to show which distance measures, together with true KPC, produce consistent collision risk assessments. We explained that what we want ideally is to have agreement between separation so that we get closest approach when we get highest probability of collision, and so that we get lowest probability of collision when we get highest separation. And so we can see that for the 99.73% minimum distance, this percentile in the distribution right here, that's the only separation measure for which we experience consistency. And we don't see that for other separation measures. Here, we see that there's really no correlation between local minimum of collision probability and of separation measures. We really don't see any agreement. And so that's a significant result, because these separation measures are used in the collision avoidance community to define safety criteria. And so yes, we may get safety from a separation sense, but not perhaps from a probability sense. Now we are going to define the collision correlation index, which is basically the correlation coefficient. Again, for those of you who are familiar with statistics, instead of dealing with the true probability of collision separation measures as samples, we're dealing with them as waves, as functions, as waveforms. And so we're essentially trying to ask the angle, what is the angle between these two functions? And so the closer this angle is to -1, the more ideal the consistency that we would have. And so we can see here some really ideal behavior where when we experience closest separation or lowest, smallest distance between agents corresponding to high probability of collision. This we would like to see. And so we were going to evaluate if this happens more generally, this intuition that we saw for this example. This chart is the main simulation result of the paper, and it shows the collision correlation index for the case of radial and cross-track motion being out of phase. The case that I'm presenting here is one of the most famous cases for passive formation flying collision avoidance. And so this is a prime example. And what we saw, we can see a lot of things. We can see first that the norm of expected relative position, which, again, as I explained before, is a statistic that we obtain during filtering, has the correct relationship, less than 0, just as often as it has the incorrect relationship. So it's completely untrustworthy, actually. And we can say that there's no relationship between the norm of expected relative position and kinematic probability of collision, which, going back a few slides earlier, that is a completely counterintuitive result. We thought, these two things are telling us the same thing. The closer these agents get to each other, the higher the probability of collision is. And we saw that that is just not true. That's just as often true as it isn't true. So for every case that it's true, we can find another case when it's not true. And so that's just not ideal. And this can tell us that we really shouldn't use separation as a measure that's consistent with collision probability. Really, these are we should think of these things as being separate. So as for the other collision separation minimum distance measures, the distances to the contours in the 3 sigma envelope, the geometric 3 sigma, 3 standard deviations away, and the equivalent contour where we have 99.73% of cases are within this gray contour. Those two measures are better. but these are the measures that are in orange and yellow. They're better, but they're not great. And on the other hand, the 99.73% minimum distance, which is the percentile in the empirical distance distribution, so that 99.73% of cases are higher than that. That has the relationship that's the most ideal. It's the closest to -1 that we see. And so out of all the separation measures that we see, this methodology is the one that has the best agreement with collision probability. And so if we were to recommend that, and we assume that collision probability is an accurate representation of collision risk, then we should go with that. In conclusion, we have presented two contributions in this work. First, projection KPCs overestimate true KPCs. This result is stated as a theorem, and it is validated through Monte Carlo simulation in an environment that's subject to quasi-Wilshire dynamics. We have also learned that approximating collision risk by a projection probability of collision is not really an adequate practice. We have also learned that not every separation measure is consistent with probability of collision. We find that the worst separation measure is the norm of expected relative position, and the best separation measure is the percentile and the empirical distance distribution, so that 99.73% of cases are higher than that. So I know that's a lot, and that's probably a little confusing, and that's a lot to digest, but these results help bridge the gap between distance-based and probability-based collision risk assessment information flying. Thank you all so much for watching this presentation, and I look forward to your questions.
Thanks so much, Ulises. Yeah, definitely it's very complex topic and not easy to understand, especially about probabilities. Even though collision is a very important aspect of the space industry nowadays, the mathematical analysis in the background is very complex. And congratulations for your work. Roxy?
Indeed, I agree with Angel. Thank you so much, Ulises, for giving us this amazing presentation. I was captivated and just into it because it's amazing. It's complex, but at the same time, something to be need to be discussed. So thank you so much for bringing this topic to us, and so we can learn more about it. And thank you for trying to make us understand it the best way we could understand it. So thank you so much for that too.
Great. So now we will open the conference for questions from the audience. And the questions can be either in Spanish or English. Ulises can speak both.
Sí, por supuesto.
Right. So if anyone has a question, okay, we have Marion. Yeah, please, you can do it by voice, Spanish or English. Puede ser en español o inglés, Marion, como quieras.
Yes, good evening.
All right.
I just tuned in. I just forgot all about the Zoom because I've been very busy. But the little bit that I've gathered, it seems about the explanation regarding possibility of collision. Is that correct?
Yes, ma'am.
Okay, collision of asteroid?
No, it's not with asteroids. So basically, let me go back here. These are basically formations of spacecraft that are flying together in formation. And so we're like the talk was about a probability of collision between. So this target spacecraft flies around the Earth or some other planetary mass in orbit in an unusual sense, and then this chaser spacecraft moves along it this way, right? And so we can have groups of more spaceships that are flying that way. And so these collision probabilities are dynamic. The results you saw are over 2 orbit periods. So what you're talking about with asteroids is a more rare event, the probability of rare events. And so I'm not necessarily dealing with that topic because these agents are expected to be close to each other constantly.
Okay. Well, thank you, and I apologize for tuning in late, and I appreciate your explanation. Thank you very much. And I'm hoping to once more tune in earlier to hear what you have to say regarding similar topics. Thank you.
Of course.
Thanks, Marion. Okay, Luis Angel, please go ahead and unmute yourself. It could be either English or Spanish.
Okay, thank you, teacher Arcia. Hello, Mr. Nunez. My question would be about how much do we have to consider the standard deviation within the movements between the constellations, basically, from each satellites?
Yeah.
Because,
Go ahead.
Yeah, because I know that we have to make a certain statistic study in order to proceed with the following formulas and begin to state our expectations over the test cases. So that's what I'm interested about.
Yeah, so that's a very good question, actually. That depends on your risk tolerance, and actually that's a subject of ongoing research that a lot of people ask me, and I wish I had an answer to that, and that would be a subject for another talk. But because, in short, there's 2 things that you have to keep in mind. One is your probability of collision tolerance. So essentially the lower you have, in a sense, if you want to be sure that you are not colliding, then you would have more certain measurements, but that does depend on your architecture, how much, like on your sensor measurement accuracy, and also your filtering techniques, what kind of filtering you're applying, but also depends on how far along you're intending to propagate, right? In this case, we're propagating pretty far away for, that's 2 orbit periods. That's, I don't know, about 3 hours. It's a very long time. And so to answer your question, it depends. So these numbers that I chose only in order to see like what results we can get. But in reality, the uncertainties that you would get would be a lot higher than this. And so the answer, it depends.
Okay, thank you very much.
Thank you. Roxy, can you see anyone else?
I don't see questions in the chat yet.
Yeah, I have some of the questions here also. Could be in Spanish, Ulises, ¿verdad?
Yeah,
entonces, sí, una pregunta. Entonces, mencionas que la probabilidad de colisión
sí.
Se está haciendo para naves que orbitan constantemente, para flight formations o constellations.
Sí, para formaciones, para el vuelo en formación de naves espaciales, sí. En este caso, las ondas, las funciones que tú ves, las verdes y las moradas, son básicamente la probabilidad de colisión entre 2 agentes. En este sentido, tenemos un agente que está en el centro de un marco de referencia en el espacio, en órbita relativa, en órbitas relativas. Entonces, este agente que se espera que esté aquí vuela en formación alrededor de este origen. Entonces, en cada instante de tiempo nosotros definimos la probabilidad de colisión que existe. Entonces, lo que estamos haciendo es comparar, digamos, en este sentido, esta es la figura que es más fácil de interpretar. Aquí yo tengo que el riesgo de colisión es alto y la separación es menos, ¿verdad? Está más cerca las dos naves espaciales, pero entre más cerca están y hay más riesgo de colisión, y se espera que si ¿cómo te explico? Los indicadores de riesgo de colisión son consistentes, que esto siempre va a ser así. Y lo que vemos es que esto no es cierto. Por ejemplo, aquí yo veo que tengo un riesgo de colisión que está alto cuando tengo una separación alta. Y veo que el riesgo de colisión está bajo cuando la separación está baja. O sea, estas dos indicadores de riesgo de colisión están en contradicción. Entonces, la idea de este trabajo que presentamos en mi asesor y yo en la conferencia de especialistas de astrodinámica en el mes de agosto, fueron medidas de separación que nos digan, que sean consistentes, por lo que se comporten así, que cuando yo tenga alto riesgo de colisión tenga baja separación, y no lo reverso. Entonces, lo que vimos aquí fue que propusimos tres medidas de separación. Una, por ejemplo, en este caso asumimos que la distribución del error es gaussiana o que es normal. Y entonces dijimos, pues, no tengo tres desviaciones estándar más allá del average, del promedio. Y entonces este punto en ese contorno es el punto que está más cercano al origen. Esa es una hipótesis. Tenemos otro punto aquí que es un punto que está con el que 99.73% de los casos están dentro de este contorno. Entonces definimos esta distancia que se supone que es una distancia corta, la distancia más corta del origen a este contorno. Y la otra es que agarramos todos los casos y decimos, ok, 99.73% de los casos son más grandes que esta separación. Entonces, ¿por qué 99.7% de los casos? ¿Por qué? Porque en una variable aleatoria que sea normal o que sea gaussiana, la probabilidad de que algo que pase más allá de tres desviaciones estándar es 1 menos 99.73% de los casos. Entonces, por eso es que definimos estas medidas estadísticas de separación para ver si son más consistentes. Y lo que encontramos es que estas tampoco son consistentes, pero esta sí es consistente. Dentro de una amplia gama de casos dinámicos que se comportan de acuerdo a la dinámica de órbita relativa de Cohesi-Wiltshire, que son el modelo dinámico más simple que existe. Entonces, eso fue lo que encontramos.
Ok, excelente. Thank you. Ok, si hay alguna otra consulta en la audiencia. Luis Ángel, ¿tienes la mano levantada o...?
Sí, correcto.
Okay.
Es referente a lo que acaba de mencionar con el sigma. ¿Hasta qué punto yo podría considerar que mi hipótesis sería una muy acertada? Porque habla que al llegar a 3 sigma ya se vuelve una probabilidad de aproximadamente 99.73, si mal no escuché. Y también en este tipo de casos, cuando yo planteo mi hipótesis nula, bueno, usted sabe
sí,
que...
sí.
Okay.
Yo entiendo por la parte de donde viene Luis Ángel, y yo no estoy usando yo no estoy usando un approach de estadística como tal, donde tengo una hipótesis que estoy haciendo testing. Yo estoy asumiendo que el error está distribuido de acuerdo a esa densidad de probabilidad. Entonces, esa asunción que yo tengo que es normal, la hago así porque si yo tengo una nave espacial volando alrededor de la otra, esa nave espacial va a medir de alguna manera, ya sea con láser o con LIDAR o con radar o con GPS o con como sea, va a haber una distribución del error. Y se asume, muchas personas asumen que al inicio es la distribución de densidades gaussiana. Entonces, en este caso, no, yo lo que te estoy diciendo de por qué se escogieron estas medidas de probabilidad es porque son análogas a medidas de confidencia que nosotros usamos en variables que son unidimensionales. Es por eso. Aunque en realidad son medidas medidas de error multidimensionales.
Pero de todas maneras, igual trabajas con la hipótesis, te planteas una nula, planteas otra alternativa y tratas de trabajar sobre esas probabilidades, ¿no?
Sí, la hipótesis nula es que que en este caso sería que la colisión no pasa. O sea, es una variable de Bernoulli. Sí, la hipótesis nula es que no hay colisión. Sí, o sea, si te entiendo correctamente, esta sería la hipótesis nula, que no existe colisión. Y la hipótesis que ocurre es que sí hay colisión. Entonces, la medida de probabilidad es la probabilidad de Bernoulli de que es del evento de que la colisión existe.
¿Cómo trabajas la parte de la lógica de conjuntos en este caso? Porque en teoría, tú sabes de que cada satélite bueno, yo lo entiendo que se manejaría como un evento independiente entre sí, porque el movimiento que ellos realicen conforme a la órbita en la cual se encuentran no va a necesariamente afectar en el otro.
Sí, la manera que yo hago eso es que yo digo que la función de densidad de probabilidad es de la posición del agente I con respecto al agente J. Y entonces, para mí la probabilidad es la cantidad de masa de probabilidad que existe dentro de este conjunto. Entonces, ya aquí yo hice la convolución de las dos posiciones y yo tengo, en vez de tener ¿cómo te explico? La posición de una y la posición de la otra, asumir independencias, hacer la convolución y tener entonces la diferencia. Yo aquí empiezo con tener la función de densidad de probabilidad de la diferencia, de la separación, de la posición relativa. Entonces, por eso yo asumo que la posición del agente J está en el origen y que esta aquí es la densidad de la posición del agente I con respecto al agente J.
En este caso, ¿hasta qué corridas serían lo más recomendable para decir uno, ok, entonces yo establezco que por ejemplo, mi hipótesis alternativa es verdaderamente la adecuada? ¿Hasta más o menos cuántas corridas uno tendría que tomar?
Eso depende porque en realidad esto, lo que tú ves aquí es open loop. Esto es estoy accesando cuál es el riesgo de colisión. En realidad yo estoy aquí estacionario al tiempo cero y yo estoy viendo en el futuro, dadas las estadísticas del estado de la gente I con respecto a la gente J, yo estoy asumiendo que eso va a ser así y entonces yo veo en el futuro cuántas órbitas más adelante está mi riesgo. Y entonces, en realidad, si yo asumo que mi estadística es cierta, entonces depende de qué tan confiables sean, tú consideres tus mediciones. Por ejemplo, si yo digo que yo nada más quiero ver en el futuro a un cuarto de órbita o media órbita o una órbita, ahí es que tú terminas. En realidad, porque esto es una herramienta de toma de decisiones, lo que tú harías es asumir esa estadística y entonces tomar la medida, la probability measure, y entonces decir, ok, si mi límite es 1 en 1.000.000, entonces si yo cruzo ese límite, entonces yo debo tomar una decisión, ¿verdad? Eso depende de cuál tolerancia de riesgo uno tenga.
Siento mucho estar preguntando mucho, con el tema de los discriminantes, ¿cuáles vendrían siendo los parámetros que tú tomarías para
I'm afraid
discriminar?
no, me lamento no entender tu pregunta.
Ok, en este
O
caso,
sea, porque lo que pasa, lo que pasa es que esto en realidad no, yo creo que hay una parte filosófica que no me he explicado muy bien. Esta simulación asume que los resultados son virtuales. Estos resultados no son reales. Estos resultados se usan en el momento cero para ver en el futuro toma de decisiones. Yo no he hecho ningún tipo de medida. Yo asumo que ya el proceso de crear el error de la posición ya ha sido hecho. O sea, ya existe un método de navegación o de filtering, se le llama. O sea, ya ha habido una medición de posición relativa, de velocidad relativa, y ya ha habido un filtrado, ya sea de Kalman o extendido, o sea, ya todo el proceso de crear la estadística ya ha sido hecho. Yo solamente estoy empezando asumiendo que yo tengo de que el proceso de crear esa estadística ya ha sido hecho.
Entonces, mientras yo no haya hecho esa estadística previa, yo no puedo proseguir a este proceso, ¿es correcto?
No, exacto. Y por eso, o sea, hay que empezar por una parte, right? Mi trabajo no es crear, no es crear esta estadística, esta función de densidad de probabilidad. Yo asumo que yo tengo ese error, que ese error alguien me lo da a mí. Entonces, normalmente en el campo de guía, navegación y control de naves espaciales, esto pasa en separado. O sea, yo tengo un equipo, me diseña las mediciones de estado y hace el filtrado y luego se lo da pasa dentro de la computadora de vuelo a un algoritmo que planea cómo corregir, y eso lo hace con la asunción de estadística. O sea, entonces alguien ya ha hecho el trabajo de crear la estadística. Entonces, esa es parte de estimación óptima. Yo aquí no estoy haciendo estimación. Yo asumo que ya la estimación ha sido hecha y que yo estoy agarrando la estadística y usando eso, yo aseso cuál es el riesgo de colisión.
Ok, una última pregunta. ¿Me podrías recordar un poco sobre la temática de I y J? ¿Cuáles vendrían, qué vendrían representando cada una de estas variables?
IJ en este sentido es la posición de I con respecto a J. O sea, I puede ser lo que sea. O sea, en este ejemplo que te di, J sería el agente que tiene una órbita circular y el agente I es el que vuela alrededor del agente J. O sea, esta notación es para que sea más general, porque es posición relativa. O sea, puede ser la posición, simplemente la posición de un agente con respecto al otro.
Ok, perfecto. Muchísimas gracias.
De nada.
Muchas gracias, Luis Ángel, por todas las preguntas interesantes. Creo que se quedaron algunas cosas pendientes también, pero no queremos robarle tanto tiempo a Ulises.
Tranquilo, tengo tiempo.
Ok. Bueno, algo que creo que preguntaba Luis Ángel era que si la medida de la posición de cada satélite o cada satélite vuela dependiendo de la posición de los demás o es independiente.
Sí, eso es parte de la definición. La parte de la definición de vuelo en formación de naves espaciales es que ellos están intentando mantener una geometría unos con respecto a los otros. Es parte de la definición. Y por eso que estos son formaciones y las constelaciones no son formaciones, porque las constelaciones mantienen posiciones absolutas con respecto al centro de la Tierra. Y en formaciones nosotros mantenemos órbitas relativas.
Ok, excelente. Muchas gracias. Bueno, creo que con eso podemos terminar, Roxy. ¿Qué te parece?
Sí, más bien muchísimas gracias a los que preguntaron y hicieron consulta. Nos ayudaron también a ir entendiendo un poco más basada en las preguntas que hicieron. Muchas gracias, Ulises, nuevamente por tu participación, por tomarte tu tiempo a esta hora, ¿verdad? A poder unirte con nosotros y darnos webinar.
De nada, a la orden. Y si tienen alguna otra pregunta, por favor, háganme saber.
Sí, ya vimos que esto al parecer puede llevar a un segundo webinar acerca del tema. Vimos muchos interesados, entonces hay mucha probabilidad alta.
Sí, sí. Sí, sí, por supuesto. Y yo con mucho gusto. En realidad, este es el futuro de la astronáutica, de vuelo
El vuelo
espacial.
espacial.
Sí, que queremos no solamente que una nave espacial vuele, seguramente, sino que varias vuelen en grupo. O sea, es un buen sueño que lo hemos visto en el área de la aeronáutica y que lo hemos visto en el área de drones, de submarinos, etcétera, y que queremos extender lo posible al campo de vuelo en formación de naves espaciales. Obviamente el ambiente dinámico es completamente diferente por sin número de razones y en algún momento hablaremos de eso, de órbitas dinámicas, la dinámica de órbitas relativas, pero hay algunas similaridades y entonces ciertos de este tipo de resultados son aplicables a sistemas autónomos en tierra.
All right, perfect.
Sí, bueno, gracias.
Okay, thank you to all of the participants, and then see you in the next special guest speaker. Okay, bye-bye. Gracias a todos. Nos vemos entonces. A los del curso, si quieren quedarse unos minutos más, podemos revisar algunos temas del proyecto final. Tenemos un par de minutos más, en caso de que ustedes así lo requieran.
Gracias, profe. Voy saliendo.
Gracias, profesor Carlos.